I want to talk about the K operator that we've been talking about in class, where to remind you that this K operator is the Hermitian version of the derivative operator. And I think where we left off was you can operate the K operator in a K vector space, where this is now an eigenvalue problem where you return the K vector space times some eigenvalue. And we could look at a matrix element. So K sub K, K prime, where we're looking at the product of a K bra, the capital K operator, operating on a K prime vector space. And since this is a eigenvalue problem, I can have the eigenvalue K prime times the inner product of K and K prime, and that gives me K prime times the delta function of K minus K prime. So that's that matrix element operating in this K space. So now what I want to talk about is introducing a new operator called X. And so I'm going to kind of draw it as a capital X with a little feet, where this X, when operating on a vector space of actual Cartesian space or space X, gives me an eigenvalue of the position X, and then the eigenvector of the position space back again. So now I can do a similar exercise that I did with the K operator, whereas if I look at the inner product of K prime, and then I transform a eigenvector of K. So basically I now have these two spaces, K and K prime, and so I operate on K, I have these two spaces, X and X prime. And so if I'm operating on the eigenvector X with my operator capital X, and then take the inner product with the space X prime, then what I should get is the eigenvalue of X, the product of X prime with X, where again this is the Dirac delta function. So I get X Dirac delta function X minus, X prime minus X. So this is kind of like a position eigenvector or a position operator that we're using. Now I could take this position operator X and operate on a function space F and transform it into some new space F tilde. So now what I can do is I can project that F tilde space onto our position space X, like so, to see what projection I get out of it. And that's the same thing as saying X, the operator X, on the space F. And now what I can do is do a change of basis using the identity and say get an integral of X operator X on a space X prime, and then I have the projection of X prime on the vector space F, and then I integrate all over the X prime space. So when I do that, what do I get? Well, I get basically the integral of X prime, and this is X prime. This is the function of F as a function of X prime, and then integrate over dx prime. This product right here of x and x prime is the delta function. So I get x prime delta function x minus x prime, the function f of a function of x prime dx prime. And now integrating this just changes the x primes into x's. So the integral of this is x times the function f of x. So in the end, what I've done is to create a transformed this function, which is now just the position times the original function back again. So in the end, what the operator capital X operating on some function space like this returns that function space back again, and then what times the value of the position X. So the interesting question now is what happens when the X operator, the position operator, operates in K space. So we could take a look at something like the product of K. So I have a K vector, the X operator operating on K prime space. So let's now expand this into a different basis. So if I integrate from minus infinity to infinity, Kx operating on the basis x, the basis x projected on the space K prime, and then I integrate over all space of x. Okay, so when I do that, x, the operator x, operating on a vector space of the basis x, just gives me x times that basis back again. So I get x times k projected with x, and then x projected on the space k prime dx. Okay, so now I can replace the products of k and x and k prime with the function, that exponential wave function. So I get x, this would be 1 over the square root of 2 pi e to the minus I kx times 1 over the square root of 2 pi e to the positive I k prime x integrated over dx. So let me make some more room, and we'll now clean up this integral. The 1 over square root of 2 pi factors I can multiply together and pull out front. So I get 1 over 2 pi, and then I get x times e to the I k prime minus k times x integrated over the space x. Okay. So if you were to do one way to solve this integral would be to take the derivative with respect to k, and when you do that and multiply by I, or basically another way of saying it is I can achieve this integral above up here if I, instead of having an x in the integral, just have e to the I k prime minus k x dx. So if you were to take the derivative with respect to k of this integral right here, then you would get the same integral which is written above. And so when I do that, this right here, oh, I'm sorry, I left out a factor of 1 over 2 pi. But the factor of 1 over 2 pi times this integral right here is also the Dirac delta function. So I could write this as I, the derivative with respect to k of the Dirac delta function k minus k prime. Or written another way, I delta prime, which means our derivative with respect to the k minus k prime. So in the end, what this means is that if I took an operator, x, the position operator I mean, and it operates on a state which is a function not of x, but of the variable k, then that's the same thing as taking the derivative with respect to k of that function g. So it's actually I times the derivative because it's now the Hermitian operator. So this operator in position, but really written in terms of the k space, is I d dk. Okay. Which is interesting because the operator k in position space, x, is minus I d dx. So there's a kind of a symmetry there between if you're using the position operator x operating in a k space, then it's the derivative times I with respect to k. But if I'm the k operator operating in position space x, then the k operator is minus I times the derivative with respect to x. So there's an interesting symmetry there. It also means that it opens up for us the possibility of working in either position space or in this new k space. And pretty soon in one of the upcoming videos, I'll explain to you what this k space really means physically.